All right. Okay. If hopefully there's people on Zoom can hear us too. If you can't, please let us know. All right. So today, this afternoon, we're going to do a hands-on session on how to image planets, how to detect them, and how to characterize them. It's a lot to do, but we'll kind of cover just the basics. Just a couple caveats before we start. One, we're using a series of open source tools. They're not the only ones out there in the community. They're the ones I'm most familiar with. But the same principles and things like that will apply to basically all of the various tools that you'll see that do similar functionality. Faustine talked about how there's multiple different PSF subtraction packages out there. We're using PyClip, but the other ones all have similar functionality. They'll have different API, but you roughly know what to look for. The other caveat is that we're going to do kind of we're gonna process real data from Keck on the 4 planets around HR 8799, detect them. We're gonna measure their properties. That's a lot of work, and we're gonna try to keep it simple. So the things that we're gonna do in this demo aren't like the most advanced publication ready, like state of the art publication ready things, right? We're gonna cover the basics about how you generally do it. There might be more advanced techniques to do all the steps that we cover, but we're gonna try to do it in a simpler way that's hopefully straightforward to understand. And then there are more advanced algorithms that you can technically can use to optimize things better. But the things that we'll do here will be good enough for this demonstration. But like a lot of Sega Summer Workshop demos, they're just meant to be kind of pedagogical, right? They're not meant to be publication grade. So you don't need you probably shouldn't go out there and publish your own version of the HR 8799 detections with exactly what we covered today. But it'll give you a taste of everything that we're going to do and you can hopefully you'll be able to see how you might be able to improve upon these things as we go on to do them in a more rigorous, more state-of-the-art way that maybe is, but we got to start somewhere and we're going to start with the basics. So hopefully you'll open this imaging exoplanets tutorial. You'll have plenty of time to work on this, so you don't need to follow along with me as I go through the tutorial. I think following along is oftentimes pretty hard and sometimes hard to pay attention while doing it, while running it. So if you want to and you think you can, feel free, but it's also feel free just to watch me do things, and then you'll have plenty of time to play with this notebook on your own. Just a reminder about setup. Before you run this imaging exoplanets tutorial notebook, you do need to run the PSF Subtraction setup notebook. And this notebook, if you're running it on Google Colab, follow the cells with the orange circle, and then you're running it on your computer, follow the cells with the blue circle. What this setup does is that it's gonna basically download all the data that you'll need to do this. Like, we're using real data on real planets, so we have to actually download Keck data. Really props out to William Thompson from University of Victoria. He actually uploaded a bunch of the Keck data for HR 8799 already processed, and everything, done all the pre-processing that you might have heard about in the morning session are ready for us to use for PSF subtraction. So we're gonna we're going to use the data that he's already generously made publicly available to the community and use it to hopefully learn a bit about PSF subtraction. So you'll basically create a drive. You'll create a folder in your Google Drive where the data is stored. The data is about a couple gigabytes in size, so just be warned that if you don't have, you'll need to have that much space in your Google Drive. And then you'll download the data. We've hosted it on iPack, so we don't DDoS his personal website and bring it down. So it's all on iPack, so that all like hundreds of you collectively downloading at the same time will not bring down the University of Victoria servers. And then for the people who are doing it on the local machine, you also need to install some packages that we'll be using. For the people that are running on Colab, you'll be installing those packages as we go through the tutorial. Okay, so presumably after you've run the setup notebook, so we're just going to go through this notebook together, and I'll explain what's happening in each of the steps. So we're going to install the PyClip package. This is the package that I developed for PSF subtraction, and we're going to use some of the tools from it. In addition to some of the tools will be a little bit black box. Some of the tools will like homebrew ourselves so that we're not just using a black box to do things. So we're gonna run pip install PyClip, and now we'll install PyClip and all the dependencies of PyClip. And then since I'm running this on Colab, I'm gonna mount my Google Drive, and this will allow me to actually access the data in my Google Drive. And I've already run these steps, so this is like a cooking show. We're just gonna skip this part. All right. So now we're going to go into the actual stuff. So we're going to import a bunch of dependencies. Not much to say here. We're going to use standard ones like NumPy, AstroPy, SciPy to do a little bit of image processing and opening FITS files. And then we're going to use a bunch of libraries in PyClip to do some various things so that we don't have to code everything up ourselves. Okay. So the first part, anytime you're doing PSF subtraction, the first thing you need to do is to read in the necessary data and grab the necessary data. This is oftentimes one of the hardest parts of PSF subtraction, is to actually find the pre-processed data and find all the information in the right place from pre-processed data. It's not something that's super well standardized in our field, although folks are trying to. But we, in general, need at least a few things. We need a time series of science data. So you think about it, remember from Faustine's talk earlier this morning, like we're looking for a temporal cube, maybe an hour long, of observations taken of the same star over time. So we're looking for what's called a 3D image cube, where you have X and Y, and your third dimension is time. And this is consisted of images taken of the system over the course of a night. This data was taken with angular differential imaging. So if you recall, the sky is rotating. So we take advantage of the fact that since the sky is rotating from our point of view, all the astrophysical sources in our images are rotating, and we're using that diversity to do PSF subtraction to distinguish the astrophysical sources from the somewhat static diffractive glare of the star. And if you download this 3D cube to your computer and open it up in a FITS viewer like DS9, you can actually scroll through the temporal cube, like a little animation, and you can actually see some of the planets rotating through the image. So I encourage you to try to do that if you want to play around with the data just a bit, just get a taste of what the pre-processed data is. It's not raw data. We've already done basic image processing like dark subtraction, flat fielding, centering, things like that. But what the pre-processed data before stellar PSF subtraction looks like. In addition to that, in addition to this 3D time series of cube, we need some auxiliary data as well. We need an image of the star not blocked by the chronograph. We need to be able to measure how bright the star is. In high contrast imaging, we often measure the flux of anything relative to the star. So we need to know what the star's flux is in order to measure the flux of anything relative to the star. So an image of the star not blocked by the chronograph or some sort of calibration source of the star is needed, such as satellite spots, in order to measure the flux ratio between the star and the planet. And the last thing we'll need is in a 1D array of parallactic angles. This is basically just an array to specify how the sky is rotating in each frame. Remember, we're talking about angular differential imaging. The sky is rotating in each frame, and we need to know exactly how fast the Earth is rotating, so we know exactly how much the planets have moved in each frame. This is needed to derotate all the images, so we can, because the planet is rotating through the sky, we need to be able to derotate all the images so the planet is all aligned at one position, so we can stack all the images at a time and see the planet land on the same pixel and actually see the detection of the planet. Okay, so that's all done for you here. In addition to doing that, we also find the star center, oftentimes in the pre-processed frame, but not always. This is something that's always a quirk of various instruments. The star may already be moved so that the star's location is exactly at the middle pixel of your detector, of your image, not your detector, of your image. So this data has already been pre-processed so that the star is already located has been shifted in pre-processing data pipeline to put the star at the center of our image. So we know that the location of the star is at half of the size of the image. Okay, so this loads up all our data, and it'll plot a couple things. This is what the image of the star looks like behind the chronograph. Well, there's not really I'm not even sure there's a chronograph in this image. There's a chron in the 20. Actually, I think this is one of the Keck chronographs. I'm not going to go into the details. But this is one of the Keck chronographs. This is the star behind the chronograph. You can see faint diffraction spots, but you can see that, on this stretch, you won't be able to see any of the planets. You can change the stretch to maybe see some of the diffracted glare of the star, but by default, the automatic image doesn't show the diffracted glare of the star. And then this is the image of the star. So this is just a calibration frame. This is an unocculted image of the star. You see it looks a lot nicer than the previous image. You can see a nice central core. This is our unocculted image of the star that we're using for flux calibration. Okay, so we're going to take all this and load it into PyClip. PyClip does this thing where we basically we have an instrument interface. We try to make everything standardized so that all this heterogeneous data from all these different instruments is standardized into a set of information that is all standardized into information that's all located at the same place. So we have this instrument class. We have this, in particular, we have this generic data class that a subclass of instrument that basically allows us to handle any arbitrary data. And as long as we pass in the image cube, the centers, and the parallactic angles, we can create a data set object for that instrument. So this is a series of data, time series of data from that instrument. We can specify the inner working angle, which we specify to be 25 pixels, and the outer working angle to 250 pixels. This is totally arbitrary. You can try smaller inner working angles. Obviously, you don't want to be too small because once you're inside the physical size of a chronographic mask, you're not going to really detect planets in there. There's no point in going too small in your inner working angle. Your outer working angle decides how far we want to do PSF subtraction. You can do the whole image. It just slows you down sometimes. So we're going to pick 250 pixels so that we're not doing the entire image, but we're doing enough of the image so we can see all 4 planets. You don't have to set this. You can set this to 9,999. You can set this to 100. Depends on what kind of field of view you want to search for planets. And then, so after that, we're basically going to run PSF subtraction. Like literally 10% into this notebook, we're going to do PSF subtraction. So it gives you a sense for, this is not everything. This is not everything. After we do this, there's a lot of stuff that we're gonna be doing. So I'm going to start running this because it's going to take a few minutes. I'm going to point out there's a lot of parameters you can do. So this is going to run clip, one of the PSF subtraction algorithms in a parallelized way. It's going to run it on this data set. It's going to output it to our current folder. It's going to name it the outputs with some prefix, file prefix, and then we have PSF subtraction parameters. We're going to so this is things you can do to kind of optimize, to kind of set up your PSF subtraction problem. Like how do you want to do PCA? We're going to break up our image into 11 annuli. We do this because close to the star, the speckles behave different than far out from the star. So we want to break out our image into different annuli because the optimization is what are the best principal components to use. It's going to be different for close into the star versus far out from the star. So this is why we break our image naturally into annuli. We're not going to break our image into azimuthal sectors. If you have something like the wind-driven a halo or butterfly effect, then you might want to break things up into different sectors, but we're going to ignore that. If you don't know what that is, it's okay. We're just going to keep that at 1. Num basis it's a pretty important parameter. This specifies the number of principal components to use to model the glare of the star. Oftentimes, we don't know how many principal components to use. This is an empirical quantity. So we pick a bunch of different values, and we're going to try and see, what's the best one. So we're going to pick 1 principal component, 3 principal components, 5, 10, 20, 30, etc. For the purposes of this demo, we're only going to look at the one with 30 principal components, but you can look back at the other ones to see how effective PSF subtraction is as we change the number of principal components. Maximum basis is telling us what's the maximum number of principal components we should compute. We're gonna not cover this in this tutorial, but this has a small effect on the efficacy of your principal component analysis. If you are curious, ask me later. We're going to use angular differential imaging because, like I said, we're going to use the fact that the sky rotates. This is the most popular way to do PSF subtraction from the ground. So we're going to use angular differential imaging. And then we have this thing in PyClip. This is different for each kind of package, but we have this movement parameter, which equals to 1. And this is in unit of pixels. This is saying if you have a science image, how far should how and the planet is going to slowly move through time as the Earth is rotating, as the sky is rotating. This is asking us how long do we want to wait until we start using images as reference images, and we're specifying here that we want to wait until the planet has rotated by 1 pixel on our detector, because we know exactly how the planet is going to move, and we're just going to we know how much the planet is going to move at any hypothetical pixel, so we can compute, for any given image, in what other images at this location will a planet have moved by 1 pixel for it, so that we don't want to use images too close in time, because the planet wouldn't have moved. So the planet is at the same location as your science image, so it just subtract this off. We don't want to do that, but we also don't want to pick only images so far away in time, because especially for adoptive objects on the ground, the PSF halo will have completely changed, and those reference images aren't a good representation of our actual image. So we want to pick something. This is the hardest thing to tweak. Is you want to have your astrophysical sources move a little bit, so it's not subtracting itself off completely, but you don't want to wait too long in time so that the astrophysical source, the reference images you're using to model the glare of the star are completely changed and no longer applicable. Yes, question? Mm-hmm. Yeah, so the question is, the PSF looks like it's 10 pixels across. We're saying the PSF can move by 1 pixel, so 1/10 of a lambda over d, and we're saying that's okay. Like, wouldn't the planet get completely subtracted anyways? And this is a totally empirical quantity to pick. Oftentimes depends on the instrument, how in units of lambda over d, how many lambda over d you want to go. Oftentimes, from my personal experience, I find that you want to pick your movement to be less than a lambda over d. You oftentimes don't want to pick 0. Sometimes 0 actually does work, but you sometimes want to pick a pretty small fraction of your lambda over d. It really depends on the data set, really depends on the instrument, really depends on how fast your AO conditions are changing. So I picked 1 here. 1 is good enough. You could probably optimize this and find a better value than 1, but a fraction of a lambda over d is oftentimes the best value for PSF subtraction. Yes. That's right. So the question is, if there are multiple planets, because the planets are rotating through as a function of angle, the ones closer to it will move slower, and that's totally true. This is why we another reason why we break up our image into 11 annuli. So for each annulus, we can have a different angular exclusion zone that corresponds to the same 1 pixel exclusion zone. So this is another reason why we want to break our image into multiple annuli, because at different separations from the star, how far the sky has rotated before you start using reference images will be a different number. Yep. And this is why we use the units of pixels rather than degrees, because we want to express things in terms of fraction of lambda over d rather than fraction of angles, which changes in terms of lambda over d as a function of separation. Okay, so this takes a few minutes, and I've rambled enough for 4 minutes that we have finished running. This is the most computationally extensive part. Once we do this, everything else should be pretty quick. And then we can plot our output image. So this here plots our output image. This is with 30 KL modes. So this is using the most number of bases we've requested. And here we've detected some planets. It can challenge you to see how many planets you see in the image. There's no arrows. Usually in direct imaging talks, there's arrows pointed at locations of the real planets, which really help guide the eye. But you can train yourself here to see how many planets you see. I'm not going to tell you. I'm sure you can figure it out. But we've detected some planets. Yeah. All right, that's the whole workshop, right? Okay, we're done. There's no more. Okay, so getting this thing's called a residual map. This is what happens after PSF subtraction. That's usually, as you see here, for how much I've scrolled down the notebook, usually about 10% of the battle. you have 90% of the battle left. So just getting the residual map doesn't mean we're ready to publish something science grade. We are able to look at this to look for by eye to look for detections, but there's a lot more we want to do with these images than just running PSF subtraction and looking at a residual map. So hopefully you see some planets. The next thing we want to do is to measure, let's say, the raw position and brightness of a planet. I'm saying raw position and brightness because this is the position and brightness measured in the data, but may not be reflective of the true astrophysical position and brightness. So I'm going to give you a hint, and this is a planet. I hope you all saw the planet. Spoiler alert. So we're going to measure the raw position and brightness of that planet. Let's see. So there are much more sophisticated ways to do this. We're going to do the most basic thing because I think it's the most transparent. We're going to fit a 2D Gaussian to it to measure the position and brightness. That's all we're going to do. You can look at this and be like, this is definitely not a 2D Gaussian, right? This, like it has these like weird side lobes. These are these negative zones. This is due to ADI self-subtraction. This is the fact that the planet is in the principal component modes due to angular differential imaging, and it is then subtracting itself off. So that's why those are the negative side lobes. Those are definitely not Gaussian. There's definitely a lot of other reasons for this is why this is not Gaussian, but we're going to approximate as a Gaussian. Like I said, there are more sophisticated ways to model the entire PSF to do like a very high fidelity PSF modeling, but we're going to skip that for now. We're just going to model it as a Gaussian. I surprisingly use 2D Gaussians a lot of times. So it's like I said, it's not the most optimal method, but it's fast and it's good enough. And like I said, we call it the raw position. We call it the raw position because the image subtraction process causes distortions. It attenuates the planet's flux. It changes its actual position. The apparent position you measure may not be the actual position of the planet. So our position and flux may be biased. Our position may be biased. The raw planet flux you measure is always going to be lower than the true planet flux in almost every case. So we'll need to do additional calibration before we can report any astrophysical values. But we got to start somewhere. So we're going to need to measure the planet flux. So how we're going to do this, we basically going to guess roughly where this planet is located. So this is the X and Y pixel value. If you can open up your the output of this in a FITS viewer, or like change the matplotlib plotting scale to kind of figure out, what is the central pixel of that planet. I'm going to give, I basically give you the answer. It's roughly about 575 pixels in X and 583 pixels in Y. We're also going to give it a guess flux so that our optimizer knows roughly how bright the planet is. And then we're just going to use a 2D Gaussian fitting routine. It's nothing fancy. It just fits a 2D Gaussian to the image. We take the output. We use our residual image. We give our guess X and Y value, and it returns the peak flux of the Gaussian that we fit for. It returns the full width half max of our PSF, and returns the X and Y value of the planets of the 2D Gaussian. So where is that 2D Gaussian centered? So we can print that out. And then once you can see we've measured the raw peak flux to be 847 counts. So that's the peak pixel flux if you fit a 2D Gaussian over the peak flux of a 2D Gaussian if you fit that 2D Gaussian to the image. We find a full width half max about 8 pixels, and we find an X and Y position at 574 and 583. So pretty close to our initial guess. But these positions mean almost nothing. What we really care about in direct imaging is always relative to the star. So we want to measure things relative to the star. So for the position of the planet, we need to measure the position relative to the star. So we know the star center. So PyClip keeps the star centers in a field, so you can output for each output image. It tells you the X and Y star center. They're all the same, actually. Spoiler alert. But star Y and star, you can get the star Y and X position. I think this should be star X and star Y. Oh, we found a bug. It's okay. There's the same value. This is why I didn't find the bug, I think, when I was testing this. These are the same value. Yeah, they're the same value, so it doesn't really matter. So what we're going to compute are what's called the separation and the position angle. The separation is literally the radial separation in pixels between the star and the planet. So you can just use the distance formula to figure that out. And then the position angle is the orientation of the star, orientation of the planet with respect to the star. And position angle is defined as the angle from north towards east. So it turns out our images are going to be I've already set up the problem for you so that the images that you see here are north is up and east is to the left. So position angle starts at 0. If you're looking with respect to the star, which is in the middle here, a position angle of 0 is up here. And then as you go down here, this is 90, this is 180, this is 270. They go back to 360 or 0. So we're going to compute the position angle of any source relative to this axis going in a counterclockwise direction with respect to the image. That's just how astronomical images are oriented typically. So this is a helpful formula that does that for you. I'm not going to, it just uses an arctangent. You can convince yourself that that's correct. I leave it as an exercise to the reader. If we want to, so this is the position angle is in degrees, which is fine, but the separation is measured currently in pixels, which is not an astrophysical unit, right? Pixel on detector means nothing in astrophysics. So we need to know the plate scale of the instrument. I'm sure Rob will tell you all about calibrating plate scales tomorrow in the calibration talk. But the plate scale for Keck is about 9.952 milliarc seconds per pixel. So that tells you if you measure something that's 1 pixel in separation, that corresponds to 9.952 milliarc seconds in separation. So here we measure something that is 94.96 pixels in separation, and we convert that with the plate scale to get a planet separation in milliarc seconds, which is 945 milliarc seconds in separation. So then we print that out here, and we've found that this planet is separated from the star at 945 milliarc seconds with a PA of 318 degrees. This is not, like I said, these are raw positions. These may be biased, but this is a good first look at roughly what is the separation between the planet and the star. But it might be biased, so we can't trust it automatically. We're going to get back to how we can figure out how much we can trust it in a second. First, we're going to talk about measuring the signal to noise ratio of the planet. So we generally want to quantify the significance of a detection, even if we identify the planet by eye. So to do this, we're going to go through 2 steps. The first step is to use a planet detection algorithm on the image. This is oftentimes a step that's skipped in the field, so that's why I say it's optional, but usually it's better to do this. And I'll show you why. Here, this is the residual map. You can use this as your planet detection map, but one thing you'll notice is that a lot of the noise in this image is like pixel to pixel salt and pepper noise. None of these fluctuations are what planets will look like, right? So even though we have brightness intensities here, none of these brightness intensities are what planets look like. Planets are these much fatter looking, much blobbier looking things. So we can use that information and basically we can smooth out this noise by cross-correlating the noise with the point spread function of a planet. And that's often called a match filter in some cases. So we're basically, we know what a planet template should look like. We're going to cross-correlate it through the entire image to figure out what things here actually look like planets. And that's what this code here does. It cross-correlates the image using the on-axis point source of the star as the PSF, the PSF of the planet as well. So we're approximating the PSF of the star as the PSF of the planet. It's usually a pretty good approximation. And here we see this is a cross-correlation map where we see that we've smoothed out that pixel-to-pixel noise and try to make a detection map based on the signals of the planet. It's not the most optimal thing that we can do. There are more optimal ways to do this, but this is a really fast way that doesn't take very long. So that's why we're doing this cross correlation with the instrumental PSF of the star. Okay, so now that we computed this detection map, we can convert this detection map into a signal to noise map. Right now, the units of the detection map are in counts, right? They don't mean much other than this is image intensity. We want to figure out for each pixel, what's the significance here? What's the how significant of a deviation from 0 are you that we think that this is a planet? So to make the detection map, we have to take our cross correlation map, which is what we produced up here, and divide it by a noise map. So for every pixel, we need to compute what the noise of at that pixel is. Usually to compute a noise map, we assume azimuthally symmetric noise. So that means that each concentric annulus around the star has the same noise properties. This is oftentimes a good approximation, but it actually turns out to be a poor approximation for this particular case. And this is because we have real planets in our data. So if we're assuming, we're basically taking a for each annulus, for each separation, we basically construct an annulus, compute the standard deviation, and use that as the noise for every pixel at that separation. However, you'll notice that a lot of these separations cross pixels where there's actually bright planet signal like this one. In those cases, we're going to estimate a standard deviation as much higher. That means that we think our noise is actually higher than what we think they are because there are planets here. So the proper way to do this is to actually mask out all 4 of these planets before computing the cross correlate, before you compute the noise map. I've left that as an exercise to the reader, just to speed things up. But you would want to do that. So all the signal to noise maps we're estimating here are going to be slightly underestimated, but that's okay. This is just a demonstration. If you are doing this on an image with no planets, then this will be perfectly accurate, but we're going to be slightly underestimating the noise because of this. And you can see that actually in the artifacts. So this is the signal to noise map here. And you can see at the separations where there is a planet, you can see these like these very faint rings, right? This is because we're now plotting in signal to noise space. And so instead of seeing pixel intensity, you're seeing for each pixel is plotting the signal to noise of that pixel. So what you're seeing here is that our signal to noises are all lower because the noise we estimate here is bigger because there is actually a planet in that annulus, which makes this entire term smaller for all pixels in that annulus, which is why everything here looks like it's like dark purple. So this is, you can make this better, mask out the planets and make a better signal to noise map, but I just show you a little bit for how we want to do this, to basically make a signal to noise map to assess, what here is a detection and what isn't a detection. And we can threshold on here. We can say everything above a signal to noise of 5, we count that as a detection. Everything below is not. The actual thresholding you pick depends on the data set that you're actually using. You shouldn't always use a signal to noise of 5. But the nice thing, what I like about signal to noise maps, is that basically you can hover over a real planet and read off the pixel value, and it tells you the signal to noise of that planet. So we can basically hover over this planet right here and read off the peak pixel value of that planet, and we can estimate the signal to noise of that planet, and we see it's about 8.6. And we know this is underestimated, again, because, again, we're estimating the noise, assuming that the pixels are also part of the noise distribution, which is not correct. It causes us to overestimate our noise. So the true signal to noise of the planet is probably above 8.6, but it's at least 8.6 in our data. And I'm just showing this again for simplicity. We will want to do this with masking out the planets when we compute a real signal to noise for a real detection. Okay, so that's how to calculate signal to noise maps. Notice how we haven't talked about injecting synthetic planets yet. Synthetic planet detection is like one of the most important parts of post-processing analysis, but you can actually compute signal to noise without injecting fake planets. You can compute signal to noise just from the signals you see in the image and the noise you see in the image. Okay, after we do that, we want to inject synthetic planets. This is to calibrate for the fact that image subtraction distorts and attenuates astrophysical signal. And the classic way to calibrate for that fact in high contrast imaging is to inject synthetic planets into the data. So let me just do this while I start talking, because this is again going to take another 4 minutes. So in order to do this, we want to inject synthetic planets at the same locations as where we want to understand how much did the PSF image subtraction process distort our astrophysical sources. The amount of image distortion changes as a function of separation, changes as a function of possibly a position angle. So you want to inject your fake planets at representative locations that you think have the same noise properties as the real planet that you want to characterize. So if I want to characterize this planet up here, I want the conventional thing to do, again, is assume azimuthally symmetric noise. So you want to inject fake planets at like all at various separations, at various position angles, but the same separation as your real planet, and measure their properties to determine how how attenuated or distorted are the planet signals after post-processing. Okay, so we're gonna do a very, very simplistic version. If you want to do this for an actual publication, you're going to need to do a lot more fake planet injections. But what we're going to do is basically only inject 2 fake planets. We're going to take the real planet that we see here. We have measured its raw position angle and raw separation. So we know roughly how far away from the star it is and what rough position. It may not be perfectly accurate. It may be slightly biased, but it's pretty good. So what we can do is, let's say, let's inject 2 planets in our data. Let's inject one at the same separation, but 90 degrees to the right, and inject one at the same separation and 90 degrees to the left. So this will, those planets should land at pixels that have the same noise property as where this planet is landing. So it allows us to kind of estimate, how distorted is the planet signal and how much noise is there in our measurement, how much uncertainty there is in the measurement. For a real analysis, you probably want to inject 10 plus planets at least. So not just one here and one here, but you probably want to inject one here, 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 here. You probably don't want to do it all at the same time because those planets are going to be overlapping and start distorting each other. So you maybe want to inject like 2 or 3 planets at a time and run this whole routine multiple times so you can inject like 10, 20 simulated planets in the data and measure their recovered properties. However, we're just going to inject 2, again, for demonstration purposes, but you can see how you could possibly take this code and inject more planets in the future. All right, so it's still running, but the key thing to note here is that we're running it with the same properties. So we're using this data set where we injected fake planets into the data, but we're using the same PSF subtraction parameters. We're using analy equals 11, subsections equal to 1, the same number of num bases, and also same movement parameter. These are all the same. We're not changing anything so that the output image we see is the same as. So we're using the same procedure on the fake planets, the simulated planets, as we are on the real planets. This will take a little bit to run. So one of the hard things is figuring out how to inject synthetic planets in our data. Like, what do synthetic planets look like? And that's where you need to have this calibration image. This image was the star without the chronograph taken for Keck. So here, that image of the star without the chronograph tells us exactly what a point source in our image looks like. So we can inject something like this, but scale it down to the planet's flux. We know that this is a very bright, our star is very bright. The planets are not going to look like the same brightness as the star, but we know the planets are probably, say, 1,000, 10,000, 100,000 times fainter. So we can scale down this image and scale it down to roughly what the planet brightness should be. And that should be basically what the planet looks like in our data. So that's what we do. And you'll see that after doing that, there are now 2 more planets in this image than before. You could I'll leave it as an exercise for you to spot the difference, but I'm sure you can figure it out. There are some extra planets in the image, and not all these are real, but you can see that the real and synthetic planets look pretty similar, right? They look like it's hard to tell a priori which ones are fake and which ones are real, unless you know the system really well and know exactly where all the planets lie. Right. That means that we've done a pretty good job at injecting synthetic planets that are accurate representations of the real planets into our data. Now that we have this residual map with synthetic planets, we can now analyze the synthetic planets and measure their properties. So like I said, the real planet was here, and we injected synthetic planets at plus 90 and minus 90 degrees. And we can measure the properties of these synthetic planets. But the key thing about the synthetic planets is that we know exactly at what position and what brightness we injected those planets at. So we can check if the measured position and measured brightness is biased in any way compared to the synthetic position. Of course, this is very hard when you only do 2 planets. You probably, again, want 10 plus planets, synthetic planets, to figure out biases and noise properties. But we're going to do this with 2 just for demonstration purposes. Okay, so we can do the same thing, and in general, you want to do the same thing. In the same way that you measured your real planet's properties, you want to measure your synthetic planet's properties. So we're going to use the same 2D Gaussian fitting routine. We know, again, where exactly we injected these planets, so we can measure exactly where we injected them and see what the flux that we measure is, what the X and Y location is, and how does that compare to what we injected. So we're going to do that here. I'm going to take really fast. Okay, so the first thing we're going to do is to measure the calibrated flux ratio of the planet relative to the star. So, okay, so sorry. So this allows us to measure the calibrated flux ratio of the real planet relative to the star. So what we can do is basically the real planet's planet to star flux ratio equals to the raw planet flux you measure divided by the star flux. This is the flux of the star from our unocculted image. But the raw planet flux here has been attenuated by a factor called algorithm throughput. This algorithm throughput is how much does the PCA process attenuate the flux of the planet. You know, it's probably something like 50% or 0.5 roughly, that order of magnitude. So the planet flux is probably lower. So if we can measure this term, we can compensate for it and boost the raw planet flux to what the true planet flux should be to then measure the planet to star flux ratio in our image. And that's an observable, an astrophysical observable we can relate back to models. So to measure this term, we can measure the planet's flux, which we have done, measure the star flux, which we did, but I didn't, it's just part of the code. I didn't show you exactly. And then what we are doing with the fake planets is to measure this term, is to measure the algorithm throughput. And how we do that is basically take the mean of the fake planet fluxes that we injected and divide that by the true planet flux that we injected that with. And you can see that our algorithm throughput is about 50%. So that 50% of the light that we injected into the image, 50% of the real planet light in our image has been removed with the PSF subtraction process. This is not, especially for angular differential imaging, this number is pretty typical, 50%. It could be as bad as 90%. It could be as good. You could lose you can lose up to say 90, 95% if you're really aggressive. If you're really conservative, you can lose maybe just 10% of your flux. But most often cases, you're losing like 50% of your flux due to the PSF subtraction process. This is okay because we're not detector noise dominated often. So we're okay with losing some planet flux to subtract off the speckles better. And then once we have this algorithm throughput term, this 0.5, we can divide it in this equation. And then this allows us to measure the planet to star flux ratio. Another advantage of having the fake planets is not only can you measure this bias term, this algorithm throughput term, you can also measure the planet flux error. So basically looking at the standard deviation of your measured planet fluxes, they should all be injected with the same planet flux. Looking at the standard deviation tells us how much noise there is in this measurement. So we can use that to quantify the planet to star ratio error. Again, with just 2 planets, this measurement is very bad, probably. It's going to be very inaccurate, but with more, as you inject more and more simulated planets, you'll have a much better measurement. You can also measure the bias and error on the separation and PA of the planet. So we can do that here. Again, you just compare the measure separation against the true separation that you inject to get the bias. You compute the error by taking the standard deviation of the measure separations, and the same thing for PA. You compare the true separation against the measure separation against the true separation, and take the mean of that to see if again they are accurate. Oops. And then you look at the standard deviation by looking again, comparing the mean, comparing the measured against the true, and looking for the scatter. And you see here we can measure. We have a bias in our separation of about negative 0.35 milliarc seconds. This is actually quite small. In particular, it's much smaller than our error. You can see our error, the spread between the 2 measurements, the 2 synthetic planets we injected, is about 1.6 milliarc seconds. So the fact that the bias is much smaller than the error probably means that we don't actually have a significant bias in our measurements, that this bias is basically 0. So we're going to, for the purposes of today, adopt 0 for our biases, but you should always do this check Sometimes your PSF subtraction algorithm does distort the astrometry. Sometimes the distortion is not significant, but you only know that by actually doing this measurement. So you should always inject your fake planets and check that this is true. All right, so we measured the signal to noise of a planet. We measured the position of the planet. There's one more thing we care about from our residual images is to measure the post-process contrast curves. Contrast curves describe the sensitivity of a data set. Basically, how faint of a planet can we detect as a function of separation. We usually use what's called the 5 sigma threshold for quantifying sensitivity, that a real planet needs to be 5 sigma above the noise. This is a purely arbitrary choice. You could be picking 7 sigma, 12 sigma, some other metric, but oftentimes we adopt 5 sigma as roughly our detection threshold. So this is what we're going to do because that's just following what we do in the literature. So we're going to generate a contrast. We're going to generate a contrast curve, but this is very similar to measuring the noise map. Basically, at every separation, we measure the standard deviation. You actually oftentimes want to do this on your planet detection maps, or you can basically use your noise maps as your contrast curves in many cases. But in this case, we're going to just show how to do it from the residual maps themselves. You basically are just going to, for each separation, look again in the annulus, measure the standard deviation of the pixel values in that annulus, and use that as your 1 sigma noise. And then we can then essentially multiply that by 5 to get your 5 sigma noise. But things are never always straightforward. In our field, we have what's called small number statistics. Basically, if we're trying to measure noise here, right close to the star, you see that all our noise is very correlated. Like, the pixel here and the pixel right next to it, they're all correlated. They all come from that same blob. So we don't actually have like 100 independent noise samples here. We have maybe 15 independent noise samples. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc. So we want to because we only have 15 independent noise samples, there's an inherent uncertainty in the measurement of standard deviation because of the few independent noise samples we have at these very small separations. So you might have heard about this small sample statistics correction from Maui 2016. And that's something that we do automatically in the PyClip measure contrast function. If we know the full width half max of our PSF, we can basically estimate for each separation how many independent samples of the noise do we have, because a speckle is roughly the size of your PSF full width half max. This is actually this is a tangent aside. You can tune away if you really don't care. It's technically a somewhat overestimate because PSF subtraction process does decorrelate your noise to some extent, so that your true spatial correlation of your speckles is actually below the full width half max of your PSF. So you actually have more samples than just the full width half max, but we can make this conservative estimate that basically you only have as many samples as assuming that your speckles are indeed as big as the full width half max of your PSF. Okay, tangent over. So we can measure the noise at each pixel. That's basically your noise map. But just like how the real astrophysical sources, the planets, are attenuated by the PSF subtraction process, so is your noise. This is due to overfitting. This is classic overfitting error. So basically, not only is our planet signal, but also our noise is actually also attenuated by overfitting. And we generally make a very good approximation that the noise is attenuated by overfitting in the same way as the planet is. And that approximation holds pretty well. So we can basically use that same algorithm throughput term we calculated from the fake planets to estimate how much did our noise also get attenuated and correct for that. So we can take our uncalibrated noise and divide it by the algorithm throughput to calibrate out for that attenuation factor. And that allows us to get a 5 sigma contrast curve as a function of separation. You'll notice this one is kind of ugly. There's a few big bumps in that contrast curve. And that's because there are real planets in the data that cause our noise to be biased. Our noise is not actually this high at this separation. It's because our noise measurement is biased because there's actually a real planet in that annulus that makes the standard deviation, that makes our noise estimate way bigger than it actually should be. So we want to, in reality, mask those planets before we do this calculation. You can mask them with numpy.nans, but we just, for the simplicity of this tutorial, we're not going to do that. Okay, so that I think is everything I wanted to share. So basically, the rest of the session is up to you. Go through the notebook, understand, roughly what's going on. You can feel free to play around with it. I talked about all these different ways we could make the notebook better. You can play around with trying to make it better, tweak some of the parameters, see what's going on. And then if you have time, you can start on some of your group project ideas. So here's 4 of them that I came up with. Depends on where you want to go. If you're more interested in the post-processing aspect, or you're more interested in the planet characterization aspect. If you're more interested in the post-processing aspect, you can look. There's actually everything we're doing here is on the 2009 data set. This is the original discovery data set of the of HR-879e, the innermost planet in the system. We also offer you a second data set, the 2021 data set. This is one of the latest images of all 4 planets in the HR-879 system. So you could download that 2021 data, run clip, do everything that we just did on that 2021 data set, and measure the signal and noise of the same planets in the 2021 data set compared to the 2009 data set. Is that 2021 data set better or worse? And the answer may differ depending on what planet you look at. But that's the first thing you can do. The second thing you can do is investigate how does our contrast curve change if we use different image subtraction parameters. So how does this curve change if we tweak, say the number of KL modes we use, the movement parameter we use, how can we improve our sensitivity or not? And then the third and fourth things are more about characterizing the planets. The third thing is you can measure the flux ratio of one of the planets, and then use that measured flux ratio corrected for algorithm throughput to get an astrophysical planet to star flux ratio, and use that flux ratio in this other notebook called Planet Isochrones, using this open source package called Species to derive planet masses for the planets in the system. And you can compare your planet masses against the literature and see how well they compare. You should do pretty well, I think. And then again, probably not good enough to publish, but you can do pretty well. And the last thing, again, we're giving you 2 epochs, so you can measure the position of a planet in both epochs, in 2009 and 2021. Measure the astrometry, measure the planet-to-star separation in milliarcseconds, measure its position angle in degrees, and then use this orbit-fitting notebook using the open source Orbitize package, which you'll probably hear a little bit more about Thursday, to perform an orbit fit and estimate things like the semi-major axis, the inclination, the eccentricity of these planets, and again, compare it to what's in the literature and how well did you do. Again, you actually do pretty well, but again, not well enough to publish a paper on it, but pretty well. Okay, so the rest of the time is up to you. Feel free to take this in however way you want. I'm here to answer any questions you have. Thanks.